Cyclic voltammetry or CV is a type of potentiodynamic electrochemical measurement. In a cyclic voltammetry experiment, the working electrode potential is ramped linearly versus time. Unlike in linear sweep voltammetry, after the set potential is reached in a CV experiment, the working electrode's potential is ramped in the opposite direction to return to the initial potential. These cycles of ramps in potential may be repeated as many times as desired. The current at the working electrode is plotted versus the applied voltage to give the cyclic voltammogram trace. Cyclic voltammetry is generally used to study the electrochemical properties of an analyte in solution. Experimental method. In cyclic voltammetry, the electrode potential ramps linearly versus time in cyclical phases. The rate of voltage change over time during each of these phases is known as the experiment's scan rate. The potential is applied between the working electrode and the reference electrode while the current is measured between the working electrode and the counter electrode. These data are plotted as current versus applied potential. In Figure 2, during the initial forward scan an increasingly reducing potential is applied. Thus the cathodic current will, at least initially, increase over this time period assuming that there are reducible analytes in the system. At some point after the reduction potential of the analyte is reached, the cathodic current will decrease as the concentration of reducible analyte is depleted. If the redox couple is reversible, then during the reverse scan the reduced analyte will start to be reoxidized, giving rise to a current of reverse polarity to before. The more reversible the redox couple is, the more similar the oxidation peak will be in shape to the reduction peak. Hence, CV data can provide information about redox potentials and electrochemical reaction rates. For instance, if the electron transfer at the working electrode surface is fast and the current is limited by the diffusion of analyte species to the electrode surface, then the peak current will be proportional to the square root of the scan rate. This relationship is described by the Cottrell equation. In this situation, the CV experiment only samples a small portion of the solution, that is, the diffusion layer at the electrode surface. Characterization. The utility of cyclic voltammetry is highly dependent on the analyte being studied. The analyte has to be redox active within the potential window to be scanned. Reversible couples equals, often the analyte display a reversible CV wave, which is observed when all of the initial analyte can be recovered after a forward and reverse scan cycle. Although such reversible couples are simpler to analyze, they contain less information than more complex waveforms. The waveform of even reversible couples is complex owing to the combined effects of polarization and diffusion. The difference between the two peak potentials, IEP, is of particular interest. IEP equals EPC, EPA. This difference mainly results from the effects of analyte diffusion rates. In the ideal case of a reversible 1E couple, IEP is 59 MV. Typical values observed experimentally are greater, often approaching 70 or 80 MV. The waveform is also affected by the rate of electron transfer, usually discussed as the activation barrier for electron transfer. A theoretical description of polarization over potential is in part described by the Butler-Vollmer equation and Cottrell equation equations. In an ideal system the relationships reduces to for an n-electron process. Focusing on current, reversible couples are characterized by IPC equals 1. When a reversible peak is observed, thermodynamic information in the form of a half-cell potential EO1/2 can be determined. When waves are semi-reversible, it may be possible to determine even more specific information. Non-reversible couples equals, many redox processes observed by CV are quasi-reversible or non-reversible. In such cases the thermodynamic potential EO1/2 is often deduced by simulation. The irreversibility is indicated by IPC per mil 1. Deviations from unity are attributable to a subsequent chemical reaction that is triggered by the electron transfer. Such EC processes can be complex, involving isomerization, dissociation, association, etc. Experimental setup. CV experiments are conducted on a solution in a cell fitted with electrodes. The solution consists of the solvent, in which is dissolved electrolyte and the species to be studied. The cell equals. A standard CV experiment employs a cell fitted with 3 electrodes, reference electrode, working electrode, and counter electrode. This combination is sometimes referred to as a 3-electrode setup. Electrolyte is usually added to the sample solution to ensure sufficient conductivity. The solvent, electrolyte, and material composition of the working electrode will determine the potential range that can be accessed during the experiment. The electrodes are immobile and sit in unstirred solutions during cyclic voltammetry. This still solution method gives rise to cyclic voltammetry's characteristic diffusion control peaks. This method also allows a portion of the analyte to remain after reduction or oxidation so that it may display further redox activity. Stirring the solution between cyclic voltammetry traces is important in order to supply the electrode surface with fresh analyte for each new experiment. The solubility of an analyte can change drastically with its overall charge. As such, it is common for reduced or oxidized analyte species to precipitate out onto the electrode. This layering of analyte can insulate the electrode surface, display its own redox activity in subsequent scans, or otherwise alter the electrode surface in a way that affects the CV measurements. For this reason, it is often necessary to clean the electrodes between scans. Common materials for the working electrode include glassy carbon, platinum, and gold. These electrodes are generally encased in a rod of inert insulator with a disc exposed at one end. A regular working electrode has a radius within an order of magnitude of 1 mm. Having a controlled surface area with a well-defined shape is necessary for being able to interpret cyclic voltammetry results. To run cyclic voltammetry experiments at very high scan rates, a regular working electrode is insufficient. High scan rates create peaks with large currents and increased resistances, which result in distortions. Ultramicro electrodes can be used to minimize the current and resistance. The counter electrode, also known as the auxiliary or second electrode, can be any material that conducts current easily and will not react with the bulk solution. Reactions occurring at the counter electrode surface are unimportant as long as it continues to conduct current well. To maintain the observed current, the counter electrode will often oxidize or reduce the solvent or bulk electrolyte. Solvents CV can be conducted using a variety of solutions. Using typical electrodes, solvents dissolve not only the analyte, often atom levels, but also electrolyte, generally at much higher concentrations. For aqueous solutions, these requirements are trivial, but for non-aqueous solutions, the choices of suitable solvents are fewer. Electrolyte the electrolyte ensures good electrical conductivity and minimizes IR drop such that the recorded potentials correspond to actual potentials. For aqueous solutions, many electrolytes are available, but typical ones are alkali metal salts of perchlorate and nitrate. In non-aqueous solvents, the range of electrolytes is more limited, and a popular choice is tetrabutalammonium hexafluorophosphate. Related potentiometric techniques, potentiodynamic techniques also exist that add low-amplitude AC perturbations to a potential ramp and measure variable response in a single frequency or in many frequencies simultaneously. The response in alternating current is two-dimensional, characterized by both amplitude and phase. These data can be analyzed to determine information about different chemical processes. Frequency response analysis enables simultaneous monitoring of the various processes that contribute to the potentiodynamic AC response of an electrochemical system. Whereas cyclic voltammetry is not a hydrodynamic technique, useful electrochemical methods are. In such cases, flow is achieved at the electrode surface by stirring the solution, pumping the solution, or rotating the electrode, as is the case with rotating disc electrodes and rotating ring disc electrodes. Such techniques target steady-state conditions and produce waveforms that appear the same when scanned in either the positive or negative directions, thus limiting them to linear sweep voltammetry. Applications: cyclic voltammetry has become an important and widely used electroanalytical technique in many areas of chemistry. It is often used to study a variety of redox processes, to determine the stability of reaction products, the presence of intermediates in redox reactions, reaction and electron transfer kinetics, and the reversibility of a reaction. CV can also be used to determine the electron stoichiometry of a system, the diffusion coefficient of an analyte, and the formal reduction potential of an analyte, which can be used as an identification tool. In addition, because concentration is proportional to current in a reversible, Nernstian system, the concentration of an unknown solution can be determined by generating a calibration curve of current versus concentration. In cellular biology it is used to measure the concentrations in living ones. In organometallic chemistry, it is used to evaluate redox mechanisms. Measuring antioxidant capacity, cyclical voltammetry can be used to determine the antioxidant capacity in food and even skin. Low molecular weight antioxidants, molecules that prevent other molecules from being oxidized by acting as reducing agents, are important in living cells because they inhibit cell damage or death caused by oxidation reactions that produce radicals. Examples of antioxidants include flavonoids, whose antioxidant activity is greatly increased with more hydroxyl groups. Because traditional methods to determine antioxidant capacity involve tedious steps, techniques to increase the rate of the experiment are continually being researched. One such technique involves cyclic voltammetry because it can measure the antioxidant capacity by quickly measuring the redox behavior over a complex system without the need to measure each component. Unregistered trademark S antioxidant capacity. Furthermore, antioxidants are quickly oxidized at inert electrodes, so the half-wave potential can be utilized to determine antioxidant capacity. It is important to note that whenever cyclic voltammetry is utilized, it is usually compared to spectrophotometry or high-performance liquid chromatography. Applications of the technique extend to food chemistry, where it is used to determine the antioxidant activity of red wine, chocolate, and hops. Additionally, it even has uses in the world of medicine in that it can determine antioxidants in the skin. Evaluation of a technique equals, the technique being evaluated uses voltammetric sensors combined in an electronic tongue to observe the antioxidant capacity in red wines. These electronic tongues consist of multiple sensing units like voltammetric sensors, which will have unique responses to certain compounds. This approach is optimal to use since samples of high complexity can be analyzed with high cross-selectivity. Thus, the sensors can be sensitive to pH and antioxidants. As usual, the voltage in the cell was monitored using a working electrode and a reference electrode. Furthermore, a platinum counter electrode allows the current to continue to flow during the experiment. The carbon paste electrode sensor and a graphite epoxy composite electrode are tested in a saline solution before the scanning of the wines so that a reference signal can be obtained. The wines are then ready to be scanned, once with CPE and once with GEC. While cyclic voltammetry was successfully used to generate currents using the wine samples, the signals were complex and needed an additional extraction stage. It was found that the ET method could successfully analyze wine unregistered trademark S antioxidant capacity as it agreed with traditional methods like TEAC, Folin Kikal-2, and I280 indexes. Additionally, the time was reduced, the sample did not have to be pre-treated, and other reagents were unnecessary, all of which diminished the popularity of traditional methods. Thus, cyclic voltammetry successfully determines the antioxidant capacity and even improves previous results. Antioxidant capacity of chocolate and hops equals, the phenolic antioxidants for cocoa powder, dark chocolate, and milk chocolate can also be determined via cyclic voltammetry. In order to achieve this, the anodic peaks are calculated and analyzed with the knowledge that the first and third anodic peaks can be assigned to the first and second oxidation of flavonoids, while the second anodic peak represents phenolic acids. Using the graph produced by cyclic voltammetry, the total phenolic and flavonoid content can be deduced in each of the three samples. It was observed that cocoa powder and dark chocolate had the highest antioxidant capacity since they had high total phenolic and flavonoid content. Milk chocolate had the lowest capacity as it had the lowest phenolic and flavonoid content. While the antioxidant content was given using the cyclic voltammetry anodic peaks, HPLC must then be used to determine the purity of catechins and procyanidin in cocoa powder, dark chocolate, and milk chocolate. Hops, the flowers used in making beer, contain antioxidant properties due to the presence of flavonoids and other polyphenolic compounds. In this cyclic voltammetry experiment, the working electrode voltage was determined using a ferrocenium-ferrocen reference electrode. By comparing different hop extract samples, it was observed that the sample containing polyphenols that were oxidized at less positive potentials proved to have better antioxidant capacity. Antioxidant capacity of the skin equals the anodic peak currents produced by a platinum multi-electrode that is placed on the epidermis can determine the Skinner unregistered trademark S antioxidant capacity. As mentioned previously, a positive aspect of cyclic voltammetry is its quickness, and this method ensured that the stratum cornuma unregistered trademark S antioxidant capacity could be determined in less than a minute. As it can be believed, skin is very important as it is the largest organ. This makes it a very good candidate for the determination of antioxidant capacity since it encounters oxidation species like ultraviolet radiation and ozone regularly. Other methods like mass spectroscopy and electron spin resonance can be used to observe oxidative stress, but they are expensive and time-consuming since tissue biopsies are usually required. Once the cyclic voltammetry is performed and followed by HPLC, results show that the skin contains the following antioxidant species, ascorbic acid and uric acid. Thus, cyclic voltammetry shows high success rate in quickly yet precisely determining the antioxidant species present on the skin. See also, voltammetry, fast scan cyclic voltammetry, electroanalytical methods, Randall-Sevik equation. References. Further reading, Bard, Alan J. Larry R. Faulkner. Electrochemical Methods, Fundamentals and Applications. Wiley. ISBN 0-471-04372-9. Zosky, Cynthia G. Handbook of Electrochemistry. Elsevier Science. ISBN 0-444-51958-0. Kissinger, Peter. William R. Heinemann. Laboratory Techniques in Electroanalytical Chemistry, 2nd edition, revised and expanded. CRC. ISBN 0-8247-9445-1. Gosser, David K. Cyclic Voltammetry Simulation and Analysis of Reaction Mechanisms. VCH. ISBN 1-56081-026-2. Compton, Richard D. Craig E. Banks. Understanding Voltammetry. Imperial College Press. ISBN 1848165,854. External links, CEM 372 Spring 2000 Cyclic Voltammetry Lab Primer. Michigan State University. Measuring surface-related currents using digital staircase voltammetry. Gamry Instruments.